This is chemistry 11th, and our today's topic is hybridization. Now, dear students, hybridization means actually the mixing of atomic orbitals of different subshells having comparable energies. That means the energies of the hybridizing these atomic orbitals, it should be comparable. There should be a slight difference in their energies. So the mixing of atomic orbitals of different subshells having uh, comparable energies within the same shell. That means the main shell should be it should be same. That means only the subshells are the same. These subshells are the same shell are involved to form this to undergo this hybridization, to form a set of new equivalent orbitals of same shape and energy. That is called as hybridization. I will repeat: the mixing of atomic orbitals of different subshells having comparable energies within the same shell to form a set of new equivalent orbitals of same shape and energy is called as hybridization. It means that the hybrid orbitals which are formed as a result of this hybridization, they have got the same shape and their energy is also same. No doubt that the atomic orbitals which are involved, they are of comparable energies. That means their energy differ in their energy, slightly differ in their energies. Now as I have told you that a covalent bond is formed between two atoms by the overlap of their half-filled atomic orbitals. Now, the number of such atomic orbitals which belong to a particular atom that takes part in overlap gives us its valency. For example, I would like to tell you here, you can see the atomic number of this oxygen atom, it is 8, and its ground state electronic configuration is 1s2, 2s2, 2px2, and y1 and z1. So if we look at it, this electronic configuration, you can see two half-filled these atomic orbitals, and these two half-filled atomic orbitals are involved in overlap with the two 1s these atomic orbitals of the two hydrogen atoms. So obviously it has got a valency of 2. So I can say that the valency of oxygen atom in water molecule is it is 2. Now again you can have here we have got this nitrogen atom with its atomic number 7, and if we look at this, this is its ground state electronic configuration, and we see that there are three half-filled atomic orbitals, and these three half-filled atomic orbitals, they are involved in overlap with the three 1s atomic orbitals of three hydrogen atoms. So it is its covalency is now the covalency of this nitrogen atom in ammonia is 3. But this principle, that is the number of half-filled these atomic orbitals, as you see in case of oxygen, you got it is two half-filled orbitals. So half-filled atomic orbitals, so it is covalency is 2. Then you can see this ammonia, it has got three half-filled these atomic orbitals, and its covalency is 3. Now uh, this principle, it cannot be applied to explain the covalency of covalency of certain elements, like we have got a beryllium, we have got this boron, and we have got this carbon. Now you can see the ground state electronic configuration of these elements. You see here carbon has got its ground state electronic configuration with atomic number 6, 1s2, 2s2, 2px1, and 2py1, and z is empty. Now there are two half-filled these atomic orbitals. So obviously it should be divalent in its compounds, but in actual practice we see that this carbon atom, it is tetravalent in all of its compounds. Similarly, if you see this boron atom, if we look at its electronic configuration, we see that its electronic configuration is 1s2, 2s2, 2px1. 2px1, and these two p orbitals y and z, they are empty, and we see only half filled this 2px orbital, so it should be monovalent in its compounds, but in actual practice it is trivalent in all its compounds. Then again you can have here the example of beryllium. So in beryllium atom we see that atomic number is 4 and its electronic configuration is 1s2 2s2 with the 2 with the p subshell, that is consisting of px, py and pz, they are all empty. So looking at its configuration, it should be its covalency should be 0, but in actual practice we see that it is divalent in its compounds. So we can see that it is divalent in its compounds. Now to explain the chemical behavior, of these elements, we have got like beryllium, boron, carbon, etc. This theory of hybridization, it was rather introduced. Now, in case of carbon, the theory of hybridization, it suggests or it assumes that during chemical combination, one of the electrons from 2s orbital, it jumps to the vacant 2pz. It jumps to vacant 2pz orbital, giving rise to four half-filled these atomic orbitals. Now these you can see here how the jumping of electrons takes place. It goes from 2s to 2pz. Now this is its excited state, and in the excited state we have got now four these half-filled these atomic orbitals. We have got 2s1, 2px1, 2py1 and 2pz1. This is in excited state. Now this is the ground state. Now these four half-filled atomic orbitals of carbon atom, they then merge together and mix up and reshuffle their energies to form an equivalent set of four hybrid orbitals of same shape and energy. They are called as sp3 hybrid orbitals. That means the new set of orbitals which is formed as a result of hybridization between this 2s, 2px1 and 2py1 and 2pz, they are of same, they are equivalent, in all respects. That means we have got their same shape, we have got their same energy. Now, as far as the promotion of the electrons or the jumping of electron from 2s to 2pz is concerned, the energy that is required for the promotion of this electron from this 2s to 2pz, it is compensated by the energy that is released when carbon atom takes part in bond formation during chemical bonding. Now, and with other atoms, that means this carbon atom, it occurs the excited state. Now now we have got these three we have got four these hybrid orbitals now formed. We have got this is from the mixing of these four atomic orbitals 2s, 2px, 2py and 2pz. The four sp3 hybrid orbitals are which are formed are of same shape and energy and are directed in space towards the corners of a regular tetrahedron at an angle of 109 degree and 28 minutes, as we see in case of methane. Now it should be noted that the bond formed by this 2s, as we see 2s this 2s hybrid orbital, it should be different from the three bonds which are formed by the three 2p hybrid orbitals. But experimental studies, or experimentally it has been found that, or it has been shown that all the four bonds formed by four sp3 hybrid orbitals of this carbon atom, they are equivalent in all respects. Now, as far as this the conditions which are essential for this hybridization, or this and atomic orbitals belonging to the same atom take part in hybridization. That means the hybridization does not take place between the orbitals of different atoms. Number two, the hybridizing orbitals must be of comparable energies. There should be a slight difference in their energies, which means that only the orbitals of different subshells within the same subshell can take part in hybridization. Now, And another point, that is hybridization takes place between the orbitals of different subshells within the same shell. The orbital, one more point is that the orbitals of same subshell do not take part in hybridization. The orbitals of the orbitals of the same subshell do not take part in hybridization because their energies are same. Now another point and another characteristics of this hybridization is that the number of hybrid orbitals which are formed is equal to the number of atomic orbitals which are involved or which take part in hybridization. Another this feature of this hybridization is that hybridization takes place only when an atom takes part in chemical bonding. So as long as the atom is in free state, it does not take part in it does not undergo hybridization, but hybridization takes place only when during chemical combination. Now another feature of this hybridization is that the hybrid orbitals formed, they are equivalent in all respects. That means they have got the same shape and they have got the same energy. Now as far as the geometry of the shape of the molecule is concerned, the geometry of the molecule or the shape of the molecule can be predicted from the type of hybridization. Now another feature of this hybridization is that hybrid orbitals are more effective in forming stable bonds. These hybrid orbitals which are formed, they are more effective or more efficient in forming stable bonds than the pure atomic orbitals. Now another feature of this hybridization, I am just giving you the characteristics or the features of this hybridization. Another feature of this hybridization is that hybridization occurs between filled as well as half filled atomic orbitals. You can see here that in case of a carbon atom, as I have shown, now there are four half-filled these atomic orbitals which result from the jumping of one of the electron from 2s to 2pz. Now these, as I have told you, they mix up and they reshuffle their energies. You can see this is 2s, it is spherical, while as these p orbitals are, they are double shaped. You have got this px, this is py, and they have got pz. Now these, they mix up together and they give rise to a set of four sp3 hybrid orbitals which are directed in space towards the corners of this tetrahedron at an angle of these 190 and 28 minutes. Now these four sp3 hybrid orbitals, they are equivalent in all respects. Then comes up the types of hybridization that we will take up in the next lecture. This is for today. Thank you very much.